Here, priority is given to the students who organize this, so feel free to ask questions, and as you ask them, I'll answer them as they show up. Again, sorry for the delay. There was a little bit of lag between the streaming software catching up with, well, actually YouTube catching up with the streaming software. This is the final exam stream, so this was set up by some of my 251 students. Basically, they just wanted a review session, so they organized it, and since they've organized it, I'm here to answer any questions you have. Not going to answer questions like what's going to be on the final exam, what is this question going to be on there, is this question going to be on there. It's not the purpose of this. The purpose of this live stream is so if you have concept questions, I can answer them. I can tell you right now the questions are going to come from, if you look at the syllabus, there's 30 student learning outcomes. You're going to have a question addressing each of those student learning outcomes. Moving through Jackson's syllabus, I'm still not very confident with determining meso compounds and calculating optical activity and polarimetry. So with meso compounds, what you're looking for is a symmetry plane. And there's two ways. For cyclic compounds, it's really easy to see if they're meso. For linear compounds, this is where you're going to need the Fisher projection. So for cyclic compounds, let's say we have this versus this. And you want to know if this was a meso complex or not. Let me make sure you actually see that. Yep. So the way that you know that one is meso is not and not the other is that look for mirror planes. So if you look at the one on the left here, the left looks just like the one on the right. And what ends up happening is that, let's say, it's 1, 2, 3, that ends up being the R. Because of this mirror plane, it's going to end up being the S. Because they look exactly the same, the R and the S have exact opposite effects on polarimetry. They rotate in opposite directions, so they cancel each other out. With this one, though, you don't see the mirror plane. So this would be meso 1,3 dimethyl cyclopentane. This case, you'd have to do the 1S, 3S, 1,3 dimethyl cyclopentane. So for cyclic, they're really easy. If you see a mirror plane and you see chiral centers, then it's meso. The linear get a bit more challenging. So this is where your Fisher projections are going to come in handy. So we've got these two compounds here, and if we draw the Fisher projections, so we got 1, 2, 3, 2, 3, 1, 2, 3. We'll do this one here, this one here. So we got CH3, 3H3H, H, H, CH3H, and here we've got CH3, CH3, H, 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 CH3, H, CH3 is in the bottom. The way that we can tell if a linear compound is meso is to look at the Fisher projection again if we see a mirror plane. So in this case, if we look at the first one, I mean, it's a little easy to see here that you got the mirror plane, but let's say for sake of argument, it was a lot more complicated. If you look at the Fisher projection, there's a mirror image. So the first one is definitely a meso 2,4-dimethyl pentane. The second one, you'd have to do the R and the S. And the reason you know it's meso, one, you don't see the mirror plane, and two, if you look at the Fisher projection, there's also no mirror plane. So again, meso just kind of boils down to, can you see the mirror planes? If you do see a mirror plane and there's chiral centers, that makes it meso. Now, as far as the optical activity, you're not going to be looking at super hard problems with this. The formula, which you're going to have access to because this is an open notes exam, the measured optical activity is the reference. In this case, D means dextrorotatory. Sometimes you'll see L, that's levorotatory. That just means it has a negative optical rotation, get negative degrees. Times the path length in decimeters, times the concentration in grams per ml, times EE over 100. Now this term here, EE, if we have 90%, we're going to write it as like 90.0. If you were to represent percent as what it is, 0.90, you wouldn't divide by 100. But all you would really be asked for in a problem like this is to find this number or the EE. Finding alpha, D, L, and C, these are all kind of problems that are more reserved for like when we're actually taking test one and we're focusing on that. But in terms of the final exam, I can assure you alpha and EE are about the only two things you're going to be really hunting after. EE, again, keep in mind this is going to be between 0 and 100%. If it is racemic, so racemic meaning equal mixtures of R and S, alpha here is by definition 0. What reagents are commonly used with saccharides and lipids? Honestly, not much. Your book gives a few examples, so cyano addition to aldoses and ketoses. It's a novelty reaction. So if you have something like and you first hit this with potassium cyanide, you can definitely get potassium cyanide, KCN, followed by water. You can get cyano addition. The problem is that you're going to get both the R and the S, and you can further heat that in sulfuric acid to give you back an alcohol. That said, when it comes to reactions of aldehyde, of saccharides and lipids, we typically don't do them. It's far cheaper just to manufacture them. So something like dextrose, sucrose, fructose, D and L and all those, you're just better to refine them because nature produces it by itself. You're pretty much not going to have any reactions of these things. The only thing you're going to really see are reactions of triglycerides, and this is saponification. So saponification, you always start out with your triglyceride, and you're going to react it with some type of nucleophile. Typically with saponification, it's OH minus. This gives you triglycerol. And the fatty acetate. Acetate. No, not acetate. Carboxylate. So fatty carboxylate. If you do this with something like methanol, which is what's used in biodiesel manufacturing, what you end up producing is the triglycerol. And the ester, amine. What is that reagent? So the one that I worked with for the sucrose, that's just potassium cyanide, KCN. It's one of the few reagents that your book even bothers to mention. You can any reaction that an alcohol does, a sugar or saccharide will also do. But again, generally speaking, we don't care about these reactions. I mean, practically they're just not useful to do because we can't be selective. So let me bring up the Orgo 2 packets, unless the Orgo 1 folks have some questions. But synthetically, reactions in organic compounds aren't usually that practical. The big ones are ring opening and ring closing, but that's just an esterification reaction. Yeah, so for the reactions of so I got it up now. So these are the reactions that you're talking about. The first one here is a saponification reaction. You've got a triglyceride here. Looks like 2, 4, 6, 7. This is going to be heptanoic acid when it finishes. Back, there you are. So again, for that first one, I erased it. So for planning. If you look at the first one, it can all, that first compound, they're all basically this structure. So here R is a hexane chain. So CH2, 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 CH3. It looks complicated just because it's all drawn out. But all this is going to do when it reacts with sodium hydroxide, which is a catalyst in H2O, this is going to hydrolyze those ester bonds to give you triglycerol and the carboxylate ion. So when you run this reaction, that first one, all you're doing is taking all those esters, breaking them apart to give you triglycerol, and give you the carboxylate ion. So here you got the hexane chain hanging off the end. It's going to be heptanoic acid. For the next one, where it switches this to methanol, MEOH, the only thing that changes is that instead of forming the carboxylate ion, you'd end up just forming another ester. So that's the only difference between the first question and the second question. The first question is traditional saponification. We're forming triglycerol and a fatty carboxylate ion. For biodiesel synthesis, which is the second one, instead of forming the carboxylate ion, we form this ester. The one beneath it, this is the reaction of KCN, followed by hydrogenation. So the first step is KCN, potassium thiocyanide. And Adrian, I'll get to your questions next. So here, the cyanide will attack this, and I'm just going to leave this all as an R just to save board space. So this will be the first thing that gets formed in this species, this H2H2O-PD barium sulfate. What this is designed to do is actually a whole bunch of steps that go on at once. The first is this H2PD. This is a Lindlar. And what it's going to do is convert our KCN into a carbon cyanide double bond. And then our H2O here will decompose this bond. And this should give us a terminal, I think it's a terminal alcohol. Not remembering off the top of my head. But basically all those, that's H2O, PD barium sulfate. The only thing that's really doing is taking that cyanide and converting it back to, I think it's an alcohol, but it may be an aldehyde. All right, so Adrian, to answer your question, could you explain elimination versus discussion? Substitution for discussion board. So for this discussion board, you had, I'm going to go off the top of my head here. I know it's sodium hydroxide, sodium chloride, and then you got tert butoxide and isopropoxide. And one you're doing it in diethyl ether, the other you're doing it in, I think H2O, DMSO, something with a high dielectric constant. So more or less you're filling this in. Now, the solvent here is going to affect whether it's a type 2 or type 1 reaction. So SN1, SN2, E1, or E2. So if we have a low dielectric aprotic solvent, this is always going to go through the bimolecular pathway. So these end up being 2s. Now, the question is whether or not this is going to do elimination versus substitution. Oops, sorry, these are all 1s. So hydroxide here kind of sits at a weird tipping point. Hydroxide can do both elimination and substitution. Typically, we say if it's small, it's going to do substitution, so it's going to be SN. If it's a big base like terp-butoxide or isopropoxide, this is going to be elimination. And the Cl here is not basic at all, so it definitely has to do the substitution. So how do you keep track of which ones they are? Well, size is going to be the big one. So this is going to be your nucleophile. And this is going to be your solvent. So if it's a little base, it's probably going to do substitution. If it's a big base, it's probably going to do elimination. If it's a nonpolar solvent, it's probably going to be a bimolecular mechanism. If it's a polar protic solvent, it's probably going to be a unimolecular mechanism. Now, that said, hydroxide is a special case. So when it comes to something like sodium hydroxide, if we have sodium hydroxide, for the most part, we're going to assume substitution. That said, if you go into Organic 2 at Wake Tech, the first reaction you use, potassium hydroxide, does actually do elimination. It doesn't do substitution. So when it comes to NOH, it's probably a mixture. Of both elimination and substitution products. So I'm kind of hoping that answered your question there. But in general, big picture, if it's big, it does elimination. If it's small, it does substitution. If it's a polar solvent, it's unimolecular, so it's that one pathway. If it's a nonpolar solvent with a low dielectric constant, it's probably going to do the bimolecular, so you can get the 2. And especially we are getting to the final, these aren't going to be ambiguous reactions. You're going to be given some pretty easy ones to figure out if they're elimination or substitution. All right, back to the Organic 2 question. And I'm not going to bother with the stereochemistry because it doesn't matter for this case. Oops, one more up. So for sodium borohydride, you should probably actually already know this. Sodium borohydride reacts with aldehydes and ketones to give you an alcohol. So this is just a refresher from the aldehydes and ketones section. The next one on page 12, this is just a mixed, oh, it's not even that, they're all the same. This is also a hydrolysis this is a saponification reaction. So the way you answer this question is the same way you answered this one, and the one beneath it is answered the exact same way. Or, so this KCN one answered the same way that this one was answered. In AOHCH3, that one is answered the same way that that one's answered. Lithium aluminum hydride does the same thing as sodium borohydride. It's going to reduce this aldehyde into an alcohol. And that's it. So if you're looking at the Organic 2 stuff in terms of the reactions, Saponification is really the only new reaction you've covered. That casein stuff is stuff back with amine chemistry. And definitely lithium aluminum hydride, sodium borohydride, that's very much the aldehyde ketone section. For E versus SN and 1 versus G, will we pay more attention to the electric constant if it's protic or aprotic? So here's a fun fact. It cannot be a protic solvent and also have a low K dielectric constant. So if you see a protic solvent, it is automatically going to favor the unimolecular pathway, so SN1 or E1. Especially if it's in water. If it's in water, it's definitely going to go through the 1 pathway. But honestly, the solvent is not going to play as big a role as 1 versus 2 pathway. The bigger factor, I would say, halogens, so dehalogenation. You're typically looking at a 2 pathway. And dehydration. You're looking at a SN1 E1 pathway specifically if there's acidic conditions. So dehalogenation, if we've got a Cl or a Br or an I, particularly if we have these two, we're probably going through a bimolecular pathway. For the dehydration, that OH group is actually pretty stable by itself, so we're probably going to favor more of a 1 pathway. This is more like your book doesn't say. This is more something I've kind of picked up on in terms of the questions that get asked and the answers and what we see. Now, another fun one, and this is something that really isn't covered in your book, anything that favors the production of water is generally a favorable reaction. So if you're going to make water, the reaction probably happens. Water is a very stable molecule. CO2 is the same way. If you're producing CO2, it's probably a favorable reaction. Yeah, I'm sorry. Like NaOH, like it's ubiquitous, but it is kind of a special case. Like it really, like you're going to do a reaction if you go to organic 2, where you use sodium hydroxide with an alkyl halide, and it does elimination. It doesn't do substitution, even though you would think it would based off of everything I've been saying, everything I've read in books, everything I've seen in literature. It's just kind of a special case. That one really depends on reaction conditions. If you're running it in aqueous sodium hydroxide solution, you're going to get substitution. If you're running with just pure sodium hydroxide, it will probably do elimination. Well, here, let's see if I can get this off. Come on, you can do it. Haha. Yeah, whenever you get a question, feel free to ask it. You don't have to worry about keeping up with where we are. Got a new banjo in addition to the one I already have, so I just got the piezoelectric off of it. So proud. This is what a banjo head looks like. So the last 2 questions regarding eliminate. Sorry, now I'm catching up with your comment. The last 2 questions I answered were Orgo 1. So SN1, E1 versus S, or elimination versus substitution, and E1, E2 versus SN1, SN2. NMR questions. All right. So we'll do the big picture with NMR, and then we'll focus down onto specific questions. So with NMR, you've got two types, 1H and 13C. And there's potentially three pieces of information you can pick up out of NMR. First is the functional groups. And this is going to come out of your chemical shifts. So we figure out the chemical shift range to figure out probably what functional group we have. So for proton NMR, 0 to 2.5, probably a CH3, CH2, CH group. If we have 8 to 9, it's probably an alcohol. Next one is the relative abundance. And that's the area. So we can figure out the relative abundance of these functional groups to each other based on their areas. So it'll tell us basically the number of protons on each functional group or the number of carbons in each functional group. Now the last one is the nearest neighbor. Basically how many of these NMR active nuclei are adjacent to each other, and this is the J coupling or the splitting. Now the thing is with proton NMR, you get most of this information. Now with proton NMR, we get the J coupling. Carbon-13 can engage in J coupling, but only if it's enriched. Meaning that all of the carbon atoms have been replaced with carbon-13. So generally speaking, within a given nucleus, within a given molecule, the odds of two carbon nuclei being next to each other are 0.01%. So there is J coupling with carbon-13, we just don't see it unless we enrich it ourselves. So, big thing with NMR, it is better to start with a model than it is to try and reverse engineer it from the spectrum. So let's say we have something like that's a little too complicated. Like this molecule here. And we want to look at the 1H and carbon-13 NMR. So it is a lot easier to take a model and decide what we should see than it is to sit back and say, okay, based on the data we have, what molecule we have. It's really hard to go back for simple molecules. So for the 1H NMR, first thing we need to do is identify the number of unique hydrogen positions. So here we've got a CH3, CH2, CH2, a CH3, a CH3, and a CH3. So if you look at these three CH3s here, we can rotate them and we can't tell these three methyl groups apart. That's why we don't have any stereochemistry on them. So we definitely have 9 hydrogens that have the same chemical shift. And on top of that, and I say 9 because we got 3, 3, and 3, they don't have any adjacent hydrogens on this carbon. So we expect a singlet with an area of 9 representing these hydrogens. Now here we have a CH2 group. So the CH2 is adjacent to 2 hydrogens, so we expect a triplet with an area of 2. Here we expect to see another triplet with an area of 3. And here we expect to see a triplet that's been split into a quartet with an area of 2. For the carbon-13, if the hydrogens are the same, the carbons are the same. So we expect to see a peak for 3 carbons correspond to those. We expect a carbon there, carbon there, carbon there, carbon there. So we expect to see 5 peaks, 1 with an area of 3 and 1 with an area of 4. Or 5 peaks, 4 with an area of 1, 1 with an area of 3. So if you look at the test 1 study material, and let me bring it up. Ha, that's the wrong class. Let me go actually to organic 1. It's like, man, when did we cover dienes in organic 1? We didn't. Getting there. So I'll bring up the desktop just so you can see this problem. So you got this problem here that says we've got an NMR spectrum here. We've got two peaks A, peak A and peak E. Peak B with chemical shift 5.36, 1.54. One is a doublet plus a quartet. The other is a doublet, and their areas are 1 and 3. And we've got 3 possibilities that are suggested here: trans 2-butene, butane, and cis 2-butene. So I'm going to draw them up on the board behind me. So we've got 2 peaks, A, B, chemical shift 5.36, 1.54. In terms of our J coupling, we've got a doublet plus a quartet. We've got a doublet, and then we've got relative areas of 1 and 3. Now, the thing about NMR is that there is not a uniqueness theorem. What that means is that many things can give the same NMR spectrum. You need context to prove that you have what you have. So when we look at this, we know that we're going to have 2 peaks. So if we look at each of these molecules, there are mirror planes. We can rotate them. And so we see that these 2 carbons are the same, and these 2 carbons are the same. We can't tell them apart. If we look at left to right or right to left, so if I close my eyes and spun this, you couldn't tell me which one I started with. So here I know I'm going to have 2 peaks. Here I know I'm going to have 2 peaks. Same thing's true here. This one's going to have 2 peaks. One corresponding to these, one corresponding to these. And the same thing's true of this one. We're going to have 2 peaks. One corresponding to those 2 hydrogens and one corresponding to those 2 hydrogens. So all 3 of these predict 2 peaks. The question is, how do we resolve which one's which? Well, off the bat, the chemical shift is wrong for an alkane. So an alkane is 0 to 2.5. But let's say you didn't have that, know that off the top of your head. Because, I mean, again, I teach the course. I know, like, I've been exposed enough. I know the chemical shifts. How would you know that it was not an alkane regardless of the chemical shifts? Well, let's look at the J coupling. So if we have a doublet, that means that we have 1 hydrogen next to this peak, next to this hydrogen. And if we have a doublet plus a quartet, it means that we've got 1 next to it, and then we've got 3 next to it. So we're looking for a molecule where one set of hydrogens only has 1 hydrogen next to it, and the other hydrogens have 1 next to them and 3 next to them. So they have hydrogens on opposite sides. So if we look at trans 2-butene, these methyl hydrogens, these CH3, have 1 hydrogen next to them. So this is where our doublet's going to come from. And if we look at this one, it's got 3 hydrogens next to it and 1 hydrogen next to it. That will give us the doublet plus the quartet. So this makes sense. And the same thing is going to be true for the cis-butene. If we look at it, our methyl group is adjacent to 1 hydrogen. So we expect this to be a doublet. And the hydrogen on this carbon atom is next to 3, which will give us a quartet, next to 1, which will give us a doublet. So that works. But if we look at this one, the butane, this one will actually give a triplet because there's 2 hydrogens next to it. And if you look at this one, it'll be a triplet because of those 2 plus a quartet. So from the J coupling, we know that butane can't work. Now what about the relative areas? Well, there's 3 hydrogens here and 1 here, so there's your 3-to-1 ratio. Here there's 3 and 2, so they have the wrong ratio. So with NMR, this is really the best way to approach it. Don't try to take the spectrum and go backwards. Don't try to generate a molecule. There's only very simple cases where that will work. Take a model, see what you would expect, the J coupling, the relative areas, the chemical shifts, and compare them to your molecule. And if it's consistent, then that's probably what that is an NMR spectrum of. In terms of organic 2, the easiest stuff to mess up. The new material that we've covered since the last exam is pretty straightforward. It's just memorization. It's all biochem. The hardest part, I would say, is keeping your reagents straight. And then the second part is, well, I wouldn't even say determining aromaticity. Aromaticity is really easy to figure out. So aromaticity, there's an old discussion board that goes through this. Figure out if it's cyclic. Yeah, you're welcome. Figure out if it's cyclic. Figure out if it's conjugated, and then do that 2n+2 rule. Do it in that order. There's no point in approaching an aromatic compound if it's doesn't have a cyclic part. The other thing to keep in mind with aromaticity, the whole molecule doesn't have to be aromatic, just that one little unit. And if that unit's aromatic, then the whole molecule is considered aromatic. But I would say keeping track of the reagents, because you have covered a lot of reactions, especially with amines. There's a lot of stuff to mess up with amines. Because with amines, if you react it with ammonia, if you're not careful, it will react with a whole bunch of things to form a diammonium salt. Amines, depending on how many hydrogens are near them, they can form an amine, which is just that carbon-nitrogen single bond. And they can form an amide, which is a carbon-nitrogen double bond. I don't think you're likely to form a cyano group, which is that C triple bond N. But again, I think the amine chemistry and the reagents, that's the hardest part. At least for me. Generally speaking, yes. And this is why, so the question got asked for naming alkyl halides. You use alphabetical order to determine the lowest C in case of like 1-chloro-5-iodopentane. This has generally been the case I found. Now, that said, as faculty, we've had a debate and we don't know the answer to it. Because your textbook says do it in the way that minimizes the first position. Well, is it in the first position in the drawing or is it in the first position of the name? Now, for me, the name would make a lot more sense because that's the hardest part to write. That said, sometimes your book, and your book does go back and forth on this, your book will do it by the drawing. So let's say you had this structure, and I can draw this structure like this. These are the same structure, but you can see that if I minimize the naming by the first unit, then if I went by this structure, I put iodine first. If I went by this structure, I put chlorine first. I think it's the name based off of everything I've read, but again, you'll see some debate on this. So you would name this as chloro, iodo, 1, 2, 3, 4, 5, 6, 7, heptane. So I would personally say it's going to be by the name. So you know the chloro comes first, so this ends up being the first. So this is 2-chloro, 6-iodoheptane. But again, sometimes you'll see books argue that, well, it's the way it's drawn. So if it's drawn this way, they would end up being 6-chloro-2-iodomethane. Stick with the naming. The one thing I have caught up checking a lot of books on this is they never give you an example where there would be an ambiguity in this regard. So it's only in hypothetical questions that we've tried to generate for additional problems where we've run into this case. But if you stick to this, write the name, then do the numbers, particularly for alkyl halides, it'll always work for test questions. The final exam is 30 questions because there are 30 SLOs. If it is an alpha or beta amine, let me look it up in the notes because I don't know that off the top of my head. Actually, I think the alpha and beta amines follow the same. Let me look it up. I'm thinking they might follow the same rules as the sugars. Oh, alpha and beta. Okay. Yeah, I'm glad I looked this up. So alpha and beta amines refer to how close they are to the carboxylic acid. Wow, that is surprisingly intuitive, actually. So if we have some carboxylic acid amine, and we're going to add some NH2 group to it, if it's added here, it's an alpha. If it's added here, it's a beta. Alpha, beta, gamma, delta, epsilon, and so forth. So the alpha beta is just how far away from it is from the carboxylic acid. Alpha ketones, same idea. If you're adjacent to the carbonyl carbon, it's an alpha. If you're two away, it's a beta. for test 1 packet 3, Orgo 1 test packet 3, could you ever send the reactions on page 67? All right, let me bring up test 3 packet. I know some of those had to be corrected. On page 16 and 17, almost there. So yeah, I think this is the one that we had to correct the key because the key wasn't correct. So definitely with page 16, you're only going to see hydride shifts. You're not going to see methyl shifts. That would make more sense if it were. So if you look at one of them, it was probably the original intent to have the problem like this. So let's say you do this under acidic conditions and you do it with a polar aprotic solvent, and the first thing you're going to do is you're going to generate your carbocation. And the question is, would you get a hydride shift or a methyl shift? And the short answer is, with this, you would get a hydride shift. So this would make a lot more sense. I think the original intent of this problem was to have a molecule like this, which in this case, you would get the methyl shift to give you that. But if we only have the hydrogen here, it's not likely that we would get, we probably would just get the hydride shift. We would get some degree of, run out of board space. You would get some of this methyl shift, but one, that's a really high energy reaction to draw. The two is that this is going to be a secondary versus a tertiary. So if you're questioning on page 16 why it would be a methyl shift and a hydride shift, it's because the key's wrong. It should be a hydride shift. Same thing's true of the ones on page 17. They should be hydride shifts, not methyl shifts. It looks like what happened was there was an intent to have a third methyl group, and then the problem got changed. Yeah, you're welcome. And again, if you need to reach out to Organic 2, feel free to. There's no territory match going on here, so if you have questions about Organic 2, you're always free to come back and access, email me, I'll give you my resources. On top of that, I still have the YouTube channel. I think it posts up, hopefully it posts upcoming live streams. But definitely this fall, there will be live streams open to anyone who wants to show up. Those of you who view my live streams know I got a lot of time on my hands when I do them. So if you want to come back and ask questions during live streams, feel free to reach out. pK and pH values, no. Especially for the biological stuff, we're not. We have tables for that. The bigger thing is just understanding the concept. All right, so we're at the end of the hour. Thanks for showing up. This will be posted to the live streams. I do kind of need to start setting up stuff for the summer. So again, if you have questions, feel free to email and reach out. Otherwise, good luck with your exams. Don't forget, they are due Tuesday at 5 o'clock. There is a hard deadline. I would not recommend waiting until Tuesday to take your exam, particularly because that's when all the grades need to start getting submitted. So try to take them early. So if you have technical issues, I've got time to address them. But if you start having technical issues, especially Tuesday afternoon, there's really not much I can do for you. All right. Take care.